Welcome back to Chem 4300. In this video, we're going to begin the topic of chemical kinetics. Now, there are two main questions that we're interested in this section. And one is, we want to know how reactants become products. You probably remember in your organic chemistry class spending hours going through reaction mechanisms. Each step in that reaction mechanism then would add up to give you an overall reaction. So we want to look at all of those elementary steps that will play a role as we work out the kinetics for a reaction. And of course, the kinetics of the reaction is really the question, answering the question, what is the time scale of the reaction? How fast are the reactants consumed? How fast are intermediates formed? How fast are intermediates consumed? And then how fast are the products formed? So you can imagine for every one of those steps in your mechanism, there's rates associated with that, and then somehow all that's going to come together to give you the overall reaction rate. So that's what our focus will be. And so let's start out by just getting familiar with some of the mathematics that we're going to have to employ as we tackle this topic. So let me first start out with just some generic chemical reaction, A and B reacting to give C and D, with stoichiometric coefficients like here, lowercase a, lowercase b, lowercase c, and lowercase d. Now, if I'm interested in the rate of the reaction, I want to know how many moles of A there are to begin with, and how fast the number of moles of A is decreasing as the reaction proceeds. So I would write down that the number of moles of A at any given instant is equal to the initial number of moles minus the coefficient A times a quantity that we're going to define as the extent or the advancement of the chemical reaction. So this is going to be the quantity that we're going to refer to tell us how far that reaction has proceeded. And we could equally refer to it in terms of how far A has decreased, or how far B has decreased, or how far C is increased, or D is increased. But we're going to create a parameter for the entire reaction, which we're going to call this Z letter here from the Greek alphabet, which is going to be called the extent of the reaction. And here I have it in terms of this particular case, but generally speaking, then the number of moles at any time of the ith species is going to be equal to the initial concentration of the ith species times the stoichiometric coefficient times the extent of the reaction, how far the reaction has proceeded. So if this is 0, then the reaction hasn't started, but as time goes on, this will go to some larger value to give you the extent of the reaction. Now, these stoichiometric coefficients, I'm going to use generically this Greek symbol nu, and when nu represents the coefficient for a product, it will always be a positive quantity. And when nu represents the stoichiometric coefficient for a reactant, say over here, then it will always be a negative quantity. So A and B, as I've written them here, if I represented them as nus, they would be minus A and minus B. C and D would be just C and D when they're represented as nus. So when I write down my reaction, I'm going to write down the extent of the reaction. I can write it in terms of any species in the reaction. I'm going to write down the extent as 1 over the coefficient times the concentration at any moment minus the initial concentration. And if I want to know the rate of the reaction, then the rate will just be the derivative of this quantity, the extent of the reaction with respect to time, and in terms of any single species involved in the reaction, it will be 1 over that stoichiometric coefficient, taking these sign issues into account, times the derivative of the number of moles with respect to time. Okay. So this is what we're going to be looking at, the rate of the reaction, and we're going to be describing it in terms of the overall rate of this particular reaction here, which is this extent term, and then that can be expressed in terms of the individual concentrations. Later we'll see concentrations, or in this case right now, just the number of moles. Now, let's take an example of this. So the rate of the reaction was that expression I gave you before. Here's a chemical reaction with corresponding stoichiometric coefficients here. So the rate of this reaction will be given by, in terms of NO2, it will be 1 over this, and it's negative because this 4, when it becomes a nu, is a negative 4 because it's a reactant. So the rate of the reaction will be minus 1/4 the derivative of the number of moles of NO2 with respect to time. Now, similarly, I could have done that for oxygen. Here, the stoichiometric coefficient is 1 or minus 1 since it's a reactant. So it becomes 1 over minus 1 times the derivative of number of moles of oxygen with respect to time. And then finally, if I wanted to do it in terms of the product, then the coefficient is 2, a plus 2 because it's a product. So it's 1 over plus 2 times the derivative of the number of moles of N2O5 with respect to time. And I can write the reaction rate using any one of these species, and it's all going to be sort of adjusted for the coefficient so that we get a rate that is just with respect to the extent of the reaction, this parameter Z. Now, as I've written it here, it's in terms of the number of moles, and I mentioned in the previous slide that sometimes we'll use concentrations, and the reason we do that is because when we're working with number of moles, we're working with extensive properties, and it's sometimes very convenient to make it intensive by dividing by the system volume. So if we take the rate up here and we just divide it by the volume, similarly here, then if we multiply that all through, then what we're really doing is we're just taking the derivative, the change in the number of moles per unit volume per unit time, and that just becomes the change in the concentration per unit time. Right? So the rate in this case is going to be an intensive reaction rate. It's concentration, dimensionality of concentration per unit time. And this notation here, which I'm sure you've seen before in square brackets, is the molar concentration of the ith species. Now, technically, if you want to be accurate, you have to use what's called activities. And in the next semester of this course, when you do thermodynamics, you'll learn more about activities. But for systems that are behaving ideally, we can use concentrations. And by ideally, again, you'll have to refer back to your thermodynamics textbook for what it means for ideal mixtures and ideal solutions. Now, for reaction rates that we're going to be looking at, they will all depend on the pressure at which the reaction is occurring, the temperature, and of course, it's going to depend on the concentration of the species. And of course, it will also depend upon the kind of phases that we're working with. Are we working with just a homogeneous solution phase? Are we working with a heterogeneous phase where it's a solution on top of a solid and the reaction is occurring on the surface of the interface between these two different phases? So there can be all kinds of variables that come into play that will determine that reaction rate. So we're going to start with just looking how that reaction rate goes with the concentration of the reactants and the products. And we will find that our reaction rates can be defined in terms of rate laws. So go back here. So this rate, we can write that it will be dependent upon the concentration of the species that are present in solution, that are involved in a reaction. It will be equal to something called a rate constant times the concentration of each of the species raised to a corresponding power. So this K is called the rate constant. The order of the reaction is the powers that we raise each of these concentrations to added up. That's called the overall order of the reaction. And the individual powers are what are called the partial reaction orders. Now, these will sometimes be integers, often be integers, but not necessarily will they always be integers. So they may change, they may be fractions at some point. The reaction order here, the alpha one, is with respect to A, so we say that it's alpha order with respect to A, it's beta order with respect to B. And these are the kind of things that we will do in the lab experimentally to work out what these reaction rates are. Again, we may not know whether that's an elementary reaction, like one of those steps in that, remember that organic reaction mechanism, one of those steps might be some elementary reaction, or you may be looking at the overall reaction that involves many steps. We're just going to write this for a reaction, not knowing whether it's an elementary one or an overall reaction. We're going to write it this way, and we'll determine it in kind of experimental measurement. Okay, and again, we'll get into more detail later why they will have this particular form, but as you might guess, it's going to depend upon the mechanism of steps that led to that overall reaction. So let's look at some simple examples just from the basis of what we just looked at here. So we know that the reaction rate in this particular case, let's say A is just going to a product. Very simple. So the reaction rate is minus derivative of A concentration with respect to time. And what we just learned in the previous slide is that reaction rate will be given by K times the concentration of A to some power. So what we're going to look at is what the solution to this differential equation looks like with different types of orders for A. So for example, let's take the simplest case. What if it's 0th order in A? So if this alpha is a 0, then that means A to the 0 is just 1. And that differential equation becomes dA dt is equal to minus K. Okay. Now we have to solve that one. It's probably the easiest differential equation we've had to solve all semester. And we see that just splitting this up and integrating this, we'll get the equation which is linear that tells us that A as a function of time is equal to the initial concentration minus K times time. So as a function of time, the concentration varies linearly with the slope of minus K. And here, in this case, then the units would be moles per liter second for this rate constant. All right, that's pretty simple. It's probably the simplest one we're going to see in this video. And if I plotted the concentration as a function of time, as I said, it's 0th order. This is perfectly linear, and the negative of the slope is the rate constant. Some examples of where you might see this kind of reaction behavior is say this reaction here, it's a gas reaction on the surface, occurring on the surface of a platinum catalyst. That's the kind of case where the reaction mechanism will lead to a 0th order rate law. Okay? Let's look at another example. Again, A goes to products, but now we'll just change that alpha coefficient to 1. Now I'm explicitly writing 1 here. You don't have to write 1. But I'm just making that for emphasis here. I'm putting the 1 down. So taking that differential equation and integrating it, you can see that that's a fairly straightforward integral, and it comes out that the log of the ratio of the concentration with respect to time over the initial concentration is equal to minus K times T. If you take the log of both sides, then you end up with this expression here. And so we see now, if it's first order, that we have an exponential decrease in the concentration with respect to time, and you see that the K, the rate constant, is going to have units of 1/seconds in this particular case. So clearly, if we took our concentration as a function of time and plotted the log of the concentration, then we would get a linear plot as a function of time where the slope is minus K. So just contrast that with the previous example of the 0th order, where the concentration as a function of time was linear. Here, the log of the concentration as a function of time is linear. So here's a plot as a function of time, and you can see here's the 0th order, which is linear, and here is the exponential decrease for a first order reaction. Both of these plotted sort of with the same scales here. Now, if I plotted the zoomed in, here's the 0th order. Here is the first order. Now you see more clearly that exponential decay. And of course, if I did a log plot, log of the concentration as a function of time, then you see here, you can see that it's dropping linearly here. Here's what that 0th order looks like on a log plot. So what is linear on a normal plot, when you take the log of the concentration, it will start looking curved. And let's zoom in here. This is what the first order looks like on a log plot versus time. So it will be linear, and the slope of this will be the negative of the rate constant. So you can see some of these different behaviors. I've also plotted second order. We'll get to in a second here, so you can sort of anticipate what's happening here. But just looking at the concentration as a function of time right away you can get some clues on what the order of the reaction is. Now sometimes, particularly in the case of first order reactions, it's very useful to define a quantity called the half-life. And that's just simply defined as the time needed for the reaction to be half complete. So if I start out with some initial concentration A, then at the half-life, my concentration A will be 1/2 of my initial concentration. That seems pretty reasonable. And if I just take my expression that I got in the previous slide by solving that differential equation for the first order reaction, then I'm going to put in for the half-life concentration, which is 1/2, put it in here. I find that log of 1/2 will be equal minus k times that half-life. So rearranging this, I get this expression, which is that the half-life is equal to log of 2 divided by the rate constant, which log of 2 is about 0.693. Now this is only true for first order reactions, but we'll use it for other types of reactions, but we won't use this definition, but we will use this definition for defining half-lives when we're talking about other types of reaction orders. But for first order, we can just look at where the concentration drops to half. 0.7 divided by the rate constant is when that time is. So you can take the time divided by, or you can flip it over, take 0.9693 divided by the half-life, and you have the rate constant. So, okay, so again, I just said that this is not true for second and third order, this behavior, but we will use this concept of half-life throughout the rest of these types of reactions. So let's take this example here. Benzene diazonium chloride undergoes a first order thermal decomposition in water at 50 degrees C with a rate constant of 0.071 per minute. So if the initial concentration is 0.01 molar, how long must it be heated at 50 degrees C to reduce this concentration by half? So we have the rate constant, we have the initial concentration, we have the formula. How long it takes is a log of 2 divided by the rate constant. So it's a log of 2 divided by 0.071 per minute. It's 9.9 minutes. Note, I didn't really even need to know that initial concentration. For the first order case, this calculation here doesn't require the initial concentration. All right, that's a very simple example. So let's look at a second order reaction where now again we have A going to products, and the difference in my differential equation here is just simply that now this becomes a 2 here in the power here. So we went from 0 for 0th order, 1 for first order, and for second order reaction this is a 2 in the exponent there. So now I'm going to write down the integral by rearranging this equation, and I'll leave it as an exercise for you to do this solution, but you can see now that the inverse of the concentration varies linearly with the time, with the slope that's equal to the rate constant. In this case now, the rate constant is liters per mole second, all right? And if I wanted to rearrange this so it wasn't inverse, it would just be the concentration as a function of time is given by this simple expression. So plotting this, just again to get you calibrated on the differences here, you can see that here's our linear 0th order as a function of time, concentration, both plotted on a regular linear scale. And then you see here's the first order exponential decay, and here we see the inverse decay for the second order. So that's a much faster drop than for the first order. Now if I plotted this on an inverse scale, so 1 over the concentration versus time, just so you can see this is what the 0th order, which is linear in a linear scale, looks like on this inverse scale. Here's what the exponential decay looks like. This is the first order here, and the green one is the second order, which is a line here, but you can't really tell because I need to zoom in. So if I zoom in, you see that the second order on a 1 over concentration plot versus time is linear. And here's what the first order looks like. Another type of reaction that is second order also would be something like this. If I have A and B reacting to go to products, then the rate, of course, will be equal to these expressions here, using either A or B for the concentrations, and that will be equal to K times the concentration A times the concentration of B. So this is partial first order in A, first order in B, but the overall reaction, the exponents for A and B are going to be 2. So that's going to make this a second order reaction. And I'm not going to, again, leave this as a homework assignment for you to solve this differential equation, but after a little bit of work, you should come up with that expression here where A and B naught are the initial concentrations. And you can see then that in this sort of a way of deriving this, that a log plot involving these quantities will be linear with a slope of the rate constant. Now, you'll notice here that this solution requires you to divide by the difference between initial concentrations. Obviously, if these two initial concentrations are equal, then this goes to infinity, and that means that the solution that you got with those initial conditions is not going to work here. You have to go back and resolve this differential equation with this initial condition, and you'll find that the two concentrations, I'll give the A one here, will vary like this, just like we saw in the previous slide. So again, a plot of the log, go back here, a log of this quantity here versus time will give you a nice linear plot where the slope is the rate constant. Okay. So that's it for this video. In the next video, we'll look at experimental approaches for measuring these reaction rates.